Well, hello everyone, and welcome to our math session on COVID-19. I called this session COVID-19, a word problem into a math word problem. My name is Obada AlSaqqa. I'm a math teacher at King's Academy. Today and together, we will be going through a small but exciting journey. It's going to be rich with mathematics. We're going to try to decipher some of the numbers that we've been monitoring every day on the news. The whole session would last about 30 minutes. It could take you longer if this all depends on how much time you have, how much you wish to go down the rabbit hole. This 10 minutes video is supposed to be like a walkthrough. You probably need to read that in conjunction with a Padlet. This Padlet is the one that you see here on the screen. The link for this one, this Padlet should be along with this video on Al-Khazna. So by the end of this session, you will be able to model like a mathematician the number of cases of infected coronavirus in several areas. So we're going to pick an area and model the number of cases there and then make some predictions in the future. Please pause now and go ahead and open that link for the Padlet so that we can jump from one to another and then go back to resume this one. This Padlet is an organizer for all the resources and links that are relevant to this session. You will see that I've set them in columns. So you will see that we will be going through column one by one from left to right. As you can see also that I have put some of these notes in yellow. Those that are in yellow are the ones that we will be following to cover this 30-minute session. The rest are all extra links and resources that you can, if you have more time to go through, but preferably at the conclusion of this session. Our focus today is around the total number of people that were tested positive for the coronavirus from the first case and until now. That's going to be studied versus time. This means that we're targeting a variable that's going to be the cumulative number of cases of each day, not the number of new cases every day. We will call this number our variable from now on. Before we start, I would like to explain that there are several methods to model in mathematics. As you can see here, I've listed them. The first one is statistical modeling or regression. This is what we're going to be talking about today and applying. The other two, number 2 and 3, are simulation and solving differential equations. If you go through these two videos, it shows how mathematicians use these ways to predict the future and analyze the different effects of various variables using simulations or solving differential equations. But for now, we're going to focus on statistical modeling. All right, let's go ahead and start with that. Statistical modeling, what we need first is, let's go and jump to the second column here, is the data. So the data that we have can be obtained from so many resources. I've picked the European CDC as our resource, and the first note here is an Excel sheet. It's a spreadsheet that you can click on, download, and open to see the data as we change it right now. So basically, I have extracted from the European CDC the number of new cases every day. That's this column. And then I've made a cumulative number for that. So that means we're adding up all the cases until this day. I have also converted the data. It used to show the date, but now I'm showing the number of days that passed from the beginning of the year. You can pause here and download this spreadsheet. You can see how you can filter for any region you may choose, or a combination of regions if you wish. All right, in order to start statistical modeling, we need three things. The first is the data, and now we have that. The second is the function that we think that best fits the line that we're studying. So this is the variable that we're studying. We call it our variable, the cumulative or the total number of cases or infected people tested positive. And in order to do so, in order to see which function works best, we're gonna check one of the countries that have passed this, which is China. If you go ahead and check China like this, you'll see how this curve starts going up rapidly or exponentially, we say, and then it slows down back again, tapers down. This behavior or this curve is usually what we call, it's very similar to an S-curve we call a logistic function. So that's the second thing that we need to do our statistical analysis. So the data, the function, and then the tool. Let's talk about the function now, this S-curve, and this is what takes us to the third column that we have, which explains the logistic function. From here, I've plotted the logistic function on Desmos. If you click on this, you will see a sample of how a general logistic function looks like. We hear in the news about exponential growth. In fact, the logistic growth is also known as restricted or inhibited or even constrained exponential growth, but it is a different function anyway. They are related, but it's a different one. So that's why it has a specific name, logistic growth function. And we teach that in pre-calculus in King's Academy. We come across this function and explain how it could represent population growth or like growth of bacteria in a petri dish. And even if the growth starts exponentially, we know that there are constraints or limits to the growth, like the size of the petri dish or the size of the city, for example, for a population. So this means that there is a cap or a limit to which they can max at as a population or growth. The same can be applied to spread of rumors that cannot exceed a total, like the total of the community where the rumor is being studied. So let's see this logistic function here. I'll tell you when you can pause and have time to play with it, but let's just explore it together. What is special about this function, let's read it first. It reads y equals c over 1 plus a times e to the power of negative kx. I suppose that we all know that e is just a number. It's not any number, it's a special number, but it's a number, so it's not actually a parameter. Whereas the parameters or the constant that we're looking at are c, a, and k. So you'll see that we have sliders here for each one of them. What's special about c is that whatever value that is, it would represent the limit. You will see here y equals c is the limit at which the function can reach as x goes to infinity, or as x increases. The other two will have a and k will have an effect on the curvature, the rate of how fast it changes, k and a. And you will see, I'm sure you have noticed by now, that we have a green point here we're calling turning point. You see that if you change the value of c, it goes up and down so that it matches half that between 0 and the max. So it's the point at which half the variable was reached. Before that, you'll see that the growth is exponential or near to exponential. You'll see that it's rapidly changing, and then it's not increasing. We don't have new cases. We have new cases, but these new cases every day are becoming less and less and less and less and less until we reach no new cases. So we have the same cumulative as we go. So this turning point is the point between an increase in the new cases to a decrease in the new cases. So this is like a summary. I would like you to pause now and go ahead to go to this link and try to play with these sliders and see how this affects the graph. Okay, so now we have both. We have the data and the model. So what do we need next? The third thing would be our tool. And our tool in this case is going to be Desmos. Desmos again, we'll pick one of the countries. I picked France, for example. You'll see that in the third column now. So there's a link for this case. Here you'll see that I've plugged in the model, but instead of equals, I've put tilde. This will help Desmos understand that we're not plugging in a function, but rather we're doing statistical modeling. Here there is a table where we have x representing time from the beginning of the year. So this is the number of days from the beginning of the year, and y is the cumulative number of cases. And then if we have this table, x1 and y1, and then we want to see what is the best fit of curve, what are the values for c, a, and k that would make this function a best fit. And that means that these points that we have, the data points, we want to minimize the difference between them and our model. And this difference is called the residuals, which are here, E1. And you'll see that this is what regression does. It crunches the number for you so that you have the best numbers of C, K, and A that would give the best line. And the values of the residuals here, you'll see that they're very close to 0. The more they're close to 0, this means the more perfectly the points match our line. And you see how they're either below or above 0. This means the points are either a little bit below or a little bit above our curvature. But instead of going through all these points to know how best fit our model is, we have a statistical variable called R squared. R squared is the number that would tell us how best our curve fits the data. And the closer that number to 1, the better our model is. So this is our goal. We want a model that has a very, very close to a value of 1. We need R squared to be very close to number 1. And from here, after this regression, you'll see that the value C is 119,000. The maximum we had was 111 this point, but the maximum we expect from this model, the maximum of number of cases that we expect from this model would be 119,000. So this extra 8,000, these are the numbers that we expect to happen in the future. And in order to talk about the confidence, level of confidence that we have, this depends on the value of R squared. And that has a certain formula, which is 1 minus square root of 1 minus R squared. So if you plug this in here, you will see that with 97% confidence, we can say that the maximum number of people that will be infected in France will reach about 120,000. So I've also added another point here, which is that green one here, which represents 99% of the total expectation, maximum expectation, so 99% of C. If you use this number to see how much time do we need to reach that value, it's going to be 124 days from the beginning of the year. That means about you're getting into the beginning of May, so that's May 3rd, 4th. So by the beginning of May, we expect with 97% confidence that we would reach 99% of our expected value of people infected. So these are the results that we can come up with for this country. I'm gonna pick another one now and show you how you can change this using the data that we have, and then you on your own you can pick another country and do the analysis, and maybe post your questions, or we can discuss the results or use it in other sessions in today's symposium. You can also add at the end of each of these tables every day, when there are new cases, you can plug in the new data. So let's say we have new data here. Let's say we have another 1,000, so we're gonna plug in 1, 1, 2. So we have a new data point here, and now everything, all the analysis has been done already. You only need to check the R squared value to be plugged in here, so that you know what level of confidence you have now. We're gonna do the same again for another country. This goes by first changing the country here. So we checked France before, right? And we took these numbers. We're gonna go, let's say, Greece. And then what you need to do is find the first time you find one case, you copy that table, and then we delete the previous one. I'm gonna paste the new one, and then one small edit, which is instead of x2, y2, we're gonna call it x1 and y1. Zoom to the data, then you have, I'm gonna check R squared here, it's 0.9987. I'm gonna plug it in here with the level of confidence we have. So with 96% confidence, we think that Greece will reach around 2,364, 65, 2,347 people by May 2nd. That's 122 days from the beginning of the year. So you can also plot the residuals if you click on plot here. So you'll see what it means, how the data is best fitting your model. And I would like to note that statistical modeling has a lot of assumptions embedded. So, for example, assuming that the countries are consistent with the measures that they have been taking throughout the virus breakout. Also, that the number of the recorded cases is true and massive testing is being done. So, one of the difficulties in studying this variable in particular is that many cases are hidden or not even recorded. This also brings the point where if you go back to the Padlet, you'll see we have so many other links for you to learn about what flattening the curve means or what breaking the wave, or there are many other jargon, and you'll see how mathematics is helpful in making decisions for leaders or business owners, anybody actually in the world. My question to you now, let me say you can also save here. So you can save your work and then change again. You'll see what you've done before in the list here. My questions to you now would be, how is the case in your country, for example, or a country of your choice or interest? And then does the logistic curve fit the data? Sometimes it does not. So check it out, make sure that it actually fits the data. You have a good value of R squared. We usually say trust your intuition when you're doing statistical regression. And then what predictions do you have for the future for this country? Share your findings or questions if you have on the discussion page. And I hope you've enjoyed this session. Thank you for attending, and I hope you've learned something new and useful. And that's it.